Okay, welcome to this debrief session on the Littlefield simulation. I will be going over scenario 1 and I'll explain everything I expect you to have learned from the scenario, review some important concepts, and this will make sure that you are well prepared to handle scenario 2. This will also give a chance to teams who may not have done so well to have the same learning as every other team. So when all the teams start scenario 2, they all start at the same level. So let's get started. When you log into your Littlefield factory, it would look like this. Now, before we proceed further, I want to tell you some things about how I set up the simulation. So each time we play the simulation, I can change the settings about the equipment, about the demand and things like that. So each time you play the scenario or you play the simulation, the data is going to be different. So what you see in this video is the data I have from the current run of the simulation. It does not mean that your data will be exactly the same. The conclusions I reach in terms of which machine is the bottleneck, in your situation, some other machine may be the bottleneck because your data would be different. So instead of focusing on the exact number, that this is the number I got a capacity of 8 or I got a capacity of 5, focus on the process, how I get to that number, and then repeat that process for your own data because your data is going to be different than the data you see here. Okay, so when you log in, you'll see your team's name. So I'm looking at the Do Nothing team. This is a very interesting team. This is a team that has been added to the simulation where no decisions are taken. To give you a baseline that if you were to take no decisions, how much money would the factory make just running on autopilot as it starts without any improvements, without any modifications? This is important because there are cases where some teams do not make the right decisions and they end up doing worse than a do-nothing team. If you don't have the do-nothing team, you have no basis of comparison to evaluate your decisions. As long as you end up with some positive cash, you might think that, oh, well, I'm not gone bankrupt, so I'm fine. But that is not the case. If you are managing a factory, and had you not been there, if the factory would have done better, then that means you actually hurt the performance of the factory instead of helping it. So Do Nothing team gives you this check. Well, is my presence, is my managing the factory actually helping? Am I making more money or not? You have to be careful though. You don't want to try to be better than the Do Nothing team all the time, especially in the beginning of the simulation, because the Do Nothing team takes no decisions. It also makes no investments. Some teams that make investments can have their money fall low initially because they spend a lot of money making investments. And then as time goes up, as their investments pay off and they recoup the money, they may have fallen below the do-nothing team, but then they go back up, right? So don't try to take it that, oh, every single day of the simulation you have to be above the do-nothing team. No. When you spend your money, even if you spend it wisely, you can fall temporarily below. And so think of the end by the end of the simulation where you want to be, not where are you at the start. So the simulation shows you how much money you have, what is your rank. So there are other teams playing the simulation. If you click on the scoreboard, it shows you the other teams, how much money they have made, shows you where the Do Nothing team is, where you are, and so it shows you your rank. This up here is the timeline. So when you're able to make decisions, when the simulation starts running, you start at day 50, not at day 0. This is because if you start at day 0, you have no data to make any decisions until several days have passed. And so you can't really do anything if we start you at day 0. So we give you 50 days of data from the factory running on autopilot, and then you take control on day 50, day 51, day 50 is passed, and then you can make changes from day 51, observing the data of the first 50 days. Then you control the factory for 168 days, which takes you to day 218. And then, the simulation stops in a way that you can't make decisions anymore, but it runs on autopilot for another 50 days. And this is done deliberately because we don't want you on day 218, because you know it's your last day, to sell all the equipment, sell all the machines, and to maximize your cash position. We want you to leave the factory in a running state. If a team was to sell all their equipment, because you know you get some money by selling your equipment, on day 218 they would not be able to meet demand on the last 50 days when the factory is running on autopilot, and then their team position would actually fall. They'll not be like the top team. So you have to leave the factory with enough capacity to manage demand for the last 50 days. Okay, so you can't just say, oh, this is my last day at work, sell the factory, right? You can't do that. Okay, you can see transaction history, all the decisions you've taken so far. Obviously, Do Nothing team has no history because it takes no decisions, right? But for your teams, you would see your decisions here. Okay, you can look at your cash position. Your starting cash was $1 million. So the Do Nothing team has actually lost a lot of money, right? It's lost more than half of the starting position, and it's mostly lost on material purchases. Okay, its revenue is very small amount, right? You've bought material for $800,000. You've only earned this much revenue. We'll talk about why that happened. And then this is the money that is earned from interest, because when you maintain cash, you earn 10% interest. Okay. You can look at your each box here represents something important. So material is your incoming, the inputs you buy to make your product, right? And these are kits, right? And it shows you your inventory management here. It shows you your inventory. Now in scenario one, you can click on all this, look at the entire history. In scenario one, the inventory is managed for you. You can see the inventory never hits zero. So you always have plenty of inventory in scenario one. In scenario two, you will have to manage inventory, and then you have to apply your thinking towards that as well. I'm not going to cover that in detail because I'll be giving away scenario two, and then you won't have to think on your own. But in scenario two, you'll be coming here to manage your inventory. Now, whenever you see any plot like this or other plots in the simulation, you can hit the download button to download the data used to make this plot, and then you can load the data into Excel to analyze it further. You can also click on that button to just see the actual raw data. This is what will be downloaded when you hit the download button, or you can click the chart button to see the chart. Okay. Orders are where you see your demand. So if you look at numbers of jobs accepted each day, this is what your demand looks like. If you look at all days, we can see that demand has a lot of variability, but it tends to trend upward, then it stays flat for a while, and then it falls down. You have 3 stations. And you go to station 1, then you do step 2 in station 2, then you do step 3 in station 3, then you go back to station 2 for step 4, and then you get completed and you go out of the factory. So completed jobs here shows you how many jobs you have completed, right, on any given day, the jobs that were completed, right? And then if you look at your revenue, you can look at all days. You can see that you were making money in the beginning, and then you talk about what happened. You stop making money. But these are important information that it gives you as plots. But you can also download the data. Then for each station, when you click in the station, it shows you the queue. Because each station has a queue. So if you look at each station, there's 2 icons here. This icon here represents the queue. The orders queued up for processing, and then the equipment icon here represents the processing. Okay, so whichever button you click on, you see all these plots here, how many machines you have. You have 1 machine here, the utilization of this station, right? And you can see that it hits 100% here at some point. You can see average kits in the queue, how the queues are, right? And so for any of these stations, you can see this information. Okay. We already talked about, you can see your cash balance here. You can also see your sources and uses of cash here, right? And then you can also download the data by hitting consolidated daily data. Okay. And you can see that that downloads everything for you in one go. You have how many average number of jobs waiting in the kits, number of jobs completed, queue sizes, utilizations. So it downloads all of the data for you to analyze in one go. Okay. What I've done is I've downloaded the data that was most important into this Excel sheet, and basically just download this file and kind of copy paste it over. So instead of having to work with this huge sheet, I'm gonna work on this sheet, and I'm gonna show you how to add the lead time data here, just to show you how I built this sheet. So if you click on finished orders, you can look at average lead time, okay, and that shows you that whatever jobs were completed that day, how long it took you to complete them. So lead time is the time taken from when the job enters the system and you receive that job as demand from the customer. That's when you start the timer, and when the job is done and you ship out the product, that's when you stop the timer. That time is the lead time, or you can call it the time taken for you to process that particular order. So whatever orders are finished in a day and you ship those out, for those orders, it calculates the lead time and it takes an average of those lead times. So for example, on a day there were 10 jobs done. It has a lead time for each of the 10 jobs, takes an average and shows you the average, right? So on day 91, for example, the average, as it's showing you on the screen, the average lead time was 10.46 days. Now that can be concerning because you're on contract one here, which you are quoting a lead time of 1 day. So you have to finish the task in 1 day to make the maximum revenue. And then, your revenue declines if you take more than 1 day, up to a maximum of 3 days. And after 3 days, the customer doesn't pay you anything. You basically lost the order, right? And so if your lead time has gone up to 10 days, that means you're not making any money on processing these customer orders. And that's what you see that happens here. If you look at your revenue, it kind of falls to zero around day at the day that we were talking about, on day 90, right? Because your lead time is so high. Okay, so how do you download the average job lead time data? So you come here, hit the download button, open the file in Excel, and then I'm just going to copy this data. Now, you'll notice that when you download data, it shows you contract 1 at the top. That's because this is the lead time for contract 1 jobs. In scenario 1, we only have 1 contract, so we don't have to worry about it. But in scenario 2, you will be able to go for higher contracts which pay more, but also have stricter requirements about the lead time. And then when that happens, it'll show you the lead time for contract 1. And then if you switch to contract 2, it'll show you the lead time for contract 2, and so on. Okay. So that's how you can get data into your Excel file to analyze it. Now, before you come in and start taking decisions, you should read this document that I posted about scenario 1 in detail. Okay. It tells you a lot of details about which days you'll have control of the factory, how much do the different machines cost, what do you get if you sell a machine, what is the interest you earn on unused cash. Why is this important? Because if you buy a machine you don't need, you're wasting money and you're not going to earn this interest on the money that you would have if you've not wasted the money. All right, so it tells you about how the revenue works, how if you deliver within 24 hours, within 1 day, you earn $1,000 per order. But if you take more than 24 hours, the revenue drops, right? And if you take more than 3 days, you don't earn any revenue. Then at the end of this document, I've given you some hints. These are questions that I would have asked you to answer in a report if I wanted you to write a report on scenario 1. So these questions are basically pointing you towards the things you should be thinking about when you are doing this scenario, right? And we'll answer a lot of these questions in this video so that you know how to think about these problems. For scenario 2, I give you these questions as well, but they're not at the end of the PDF for scenario 2. They will be in the report template, because scenario 2, you have to answer questions like these to write your report. A very, very important tip. Okay. remember to read those questions from the report template of scenario 2 before you take decisions in scenario 2, because those questions will guide you towards certain important things to think about. Okay. Okay, so let's continue. One thing I want to point out in this document is that it gives you, important data points, like the numbers in it are important. Okay, but it also gives you some important context around the demand. So if you look on page 2 at this paragraph, you have important context from the marketing department that's saying that we expect the demand to grow at a constant rate for 5 months. A month has about 30 days, so 5 months is about 150 days, right? So for the first 150 days, we expect growth in demand. And it's stabilized for another month, like, be flat for about 30 days, and then start to fall and start to drop after that. Okay, so after day 180, so the last days that you manage the factory, 180 to 218, you might see the demand to drop. Okay, so something like this can be very useful, because if you are sitting, let's look at the demand. If you're sitting at day 50, somewhere here, you know what to expect. You know the demand is going to go up to day 150. Okay, so it doesn't exactly follow what the marketing department said, but approximately follow. That kind of grows till day 95 instead of 150, then kind of flattens out, right? So it only grows for like 3.5 months. And then it's flat for longer than a month, but the marketing was approximately right, that it grows initially, it becomes flat, and then it starts to fall around day 200. Okay? So what this tells you is that the overall pattern for the demand might be given in the write-up, and that can help you plan for how you're going to manage the simulation. The other thing to keep in mind is that I will tell you on Canvas about the time scale of the simulation. So sometimes, especially for the training scenario, I like to run it where half an hour of real world time is one simulation day. So every hour, the clock advances by 2 simulation days on the simulation. But sometimes, especially for scenario 2, and if it's a full-time course, I like to run it at half of that speed. So I like to run it at 1 hour of real life time is one simulated day. Okay, so when that happens, the total simulation runs for a week. When I'm running it at 1 hour real time is one simulated day. But if I run it at 1 hour equals 2 simulated days, and the simulation runs for 3.5 days, 3 days and 12 hours, right? So it'll be announced on Canvas what time scale we're working on. So you have to keep that in mind, because it's good to take decisions in the first half of the simulation. So the first 3 days, if it's running for a week, or the first 1 to 2 days, if it's running for 3.5 days. Because if you start, adding machines or doing other stuff at the end, you have to ask yourself, do I have enough time left to benefit from these investments? Is this new machine gonna process enough orders to pay for its cost, right? And so that becomes a concern towards the end of the simulation. Okay, so without further ado, let's start talking about the analysis part. So how do we make money in the simulation? Okay. So if you read this document, it explains that you make money by completing the customer order within the promised lead time. And in the simulation, when you open anything, it tells you current contract is quote time is 1 day, maximum lead time is 3 days. If you finish in 1 day, as the write-up explains, you earn $1,000 in revenue. If you complete in 1 to 3 days, you earn less than 1,000, and at 3 days or more, you earn $0. So what that tells me is I have to keep the lead time under control. So a very important metric that you should track is daily average lead time. And you want to make sure this stays under 3 days. So here it's hitting 3 days about on day 70. It stays under 3 days for contract 1. But even, close to 3 days, you're really earning very little money. It should ideally be 1 or lower for contract 1, because that's what you have promised the customer. So, you have to keep the lead time under control. So this is an important metric to track. Okay? Related to this, if you keep the lead time under control, it's going to be average revenue per job. And you can see here that up till about day 69, you're making some money, $44 or whatever, some small amount of money. But after that, you're making zero money. Okay? And that is because your lead time is too high. So that's also an important metric to track. So what impacts lead time? Well, as we mentioned, as orders come in and they pass through this process, they go out, it's a time taken to go through our factory. That's our lead time, right? So the equipment doesn't takes the same amount of time for each piece it processes. So why is the lead time growing? It has to do with queues. Your lead time is your lead time is growing, is probably because things are spending a lot of time waiting in queues. So we saw our lead time grow. Logically, that should be coupled with your queues growing as well. So because queues growing longer is what causes longer lead times. If you look at average kits in your queue, and you see that it is growing, and it really blows up after day 50 or 60. At day 70, 80 is really blowing up. So your queues are blowing up, they're increasing too much, which is causing your lead time to increase because bots are spending more time in the queue, right? So that's station 1. If you look at station 2, queue also going up. And station 3. So they sometimes go up by a lot, but then they fall, so they're kind of all over the place, but they're not at least consistently growing in the beginning. Okay, so these are the important metrics you want to keep track on, the queues. Now, why do queues grow? Why do queues form? Why do queues grow? That's an important question because we saw you want to keep track of lead time, average revenue per job. That is affected by queues. So why are queues forming? Why do we have queues in our system? Okay, so all of you have probably experienced traffic jams forming on a highway. If there's an accident or there's lane closures, right? And traffic jams are queues. So what happens if we have this highway and this lane is closed? Okay. When do these queues form? Well, if the inflow of traffic exceeds the capacity of these two lanes, the remaining lanes, then queues will start to form. But if it's not rush hour, there are very few cars coming, then even with lane closure, there'll be no queues, right? So that's the insight you can take, that whenever demand is greater than equal to capacity, your queues will start to increase. Okay. That does not mean when demand is slightly below capacity, there's going to be no queues. There still might be queues, but they will usually be manageable. They'll not grow consistently. They might grow a little bit and come down, then grow, then come down, right? But they wouldn't grow consistently. But if demand equals capacity or is more than capacity, then queues will tend to grow. Okay. You might ask me, well, why does demand being equal capacity, the queues tend to grow? Demand being equal to capacity should be fine. Well, that's because things don't happen at regular intervals. So it's not like, okay, let's say capacity is 10 units per hour, okay, and demand is 10 units per hour, okay. It's not that these 10 units will come equally spaced out within the hour. All 10 may arrive in the first minute, or 5 might come and then nothing might happen, and then 5 might come in the last minute of the hour, right? And so you can't handle 5 at the same time. You handle 10 in 1 hour. It takes you 6 minutes to handle 1 unit. So if 5 come, it's going to take you 30 minutes to handle 5. So if 5 come together, the 5th person is waiting half an hour, right? And so when demand equals capacity, queues can be pretty long. But if demand is obviously more than capacity, then queues just keep growing, right? So both these cases are usually not ideal. Usually you want to keep your capacity above demand. So capacity should be more than demand. How much more you have to decide on, how much your average waiting time you are willing to live with. If that capacity is slightly above demand, the waiting times will be, you can estimate them using math or simulation. There'll be some waiting times. And if capacity is well above demand, the waiting times will be very low, right? So, but this is what you aim for. This is green, this is good, and the red, this is no good, okay? So probably what's happening is that our demand is exceeding our capacity for our queues to start to blow up at some of our stations, right? Okay, so how do I know exactly what's happening? So if you look at these 3 stations, I have a process something like this. We have 4 steps. So this goes here, and then you go out, you're done, right? So if either step 2 or 4 is the bottleneck, station 2 basically is the bottleneck. You'll see a lot of queues here. And if station 3, doing step 3 is the bottleneck, you see a lot of queues here. Okay. So the good news is we have multiple ways to identify the bottleneck. Okay. Identify the bottleneck. One way is to look at queues, because the longest queue should be right in front of the bottleneck, right? So this you should know from the theory we have covered in class. So let's examine the queues. So station 1, okay. After day 50, the queue starts to blow up and goes up to about 500 on day 82, okay. Station 2. Wow, look at station 2. The queue goes up to 6,000. Around day 80 is like 2,500. It's way more than station 1. Okay. So between station 1 and 2, station 2 has the longer queues around day 80, day 50, and that, initial days. And then even afterwards, it has the longest queue. And then if I look here, this is the shortest queue. It spikes sometimes to 500, but usually it's below 100. Or at least below 200 or 300, right? So it's the smallest queue. Okay? So just based on the queue length, I would say station 2 is the bottleneck. Okay? So the queues tell me station 2 is the bottleneck. That's where the longest queue is. Now another way to identify the bottleneck is to look at utilizations, the machine utilization at the stations, because the bottleneck station would have the highest utilization. Why? Because the capacity of the bottleneck determines the capacity of the whole system. The bottleneck is the one where there's no idle time. Every place else should have a little bit of idle time, unless demand exceeds their capacity as well, right? So usually you'll see some idle time at non-bottleneck stations, but there are situations when the non-bottleneck station is the first station. And even though it's not the bottleneck, it's also capacity constrained because demand is more than its capacity. So you can see 100% utilization at a non-bottleneck as well, especially if it's coming before the bottleneck. After the bottleneck will only release things at its capacity. So if the other stations have higher capacity, you will not see a utilization of 100%. So let's examine the utilizations. So if you look at station 1, you can see the utilization goes up to 100%. It stayed at 100% for a very short amount of time, only a few days, some days here, then it falls again. So the demand does exceed the capacity here. So this could potentially, it is capacity constrained for some of the days here, right? Because the utilization is hitting 100%. So this could be the bottleneck, but let's look at the other stations too. And it starts to hit utilization of 100% day 58. So day 58 is when it starts to hit 100%. Okay, let's look at station 2. Yeah. Oh, I opened the queue, not the utilization. I'll look at the utilization. Okay, wow. So also on day 58, it is using 100% and it stayed at 100%. So this clearly shows you that this is the bottleneck. It has the highest utilization overall, because station 1, the utilization did start to fall a little bit, or did fluctuate after hitting 100%. This just hits 100% and goes through. Capacity is way over, the demand is way over, more than the capacity of this station. And we look at the utilization of station 3. Right, and this is also all over the place, sometimes hitting 100%. So this is getting capacity constrained on some of the days because demand is variable, but only on the peak demand days. Otherwise, its utilization is not 100%. So looking at utilization, we can clearly see that station 2 is the bottleneck. Once it hits 100% utilization, it kind of stays there. It's at 100% utilization for the most frequently. And so, we can say that this is the bottleneck. The third way we can identify the bottleneck is to actually calculate the capacity. This is the analytical part, and compare it with, and the bottleneck is the station with the lowest capacity. So for each station, we can calculate the capacity, or estimate it at least, and then we can see which one has the lowest capacity. Okay, so that's what we're going to do next in Microsoft Excel. Okay, so to do the capacity calculation, I need to explain something first. Okay, so what do we have? We have a utilization of the machines. We have data on that the simulation gives us. And we kind of can also know how much did the machine produce, because we have the output of each day, right? So each station we know is producing about the output of each day, especially in the beginning when there's not a lot of queues in the system. So we have the output. So how are output and utilization related to capacity? Ask yourself this question, okay? If a station or a machine, okay, or a station works at 100% utilization, so they have no idle time, they work the whole day, the whole shift, okay, and they produce 20 units of the product. So if by working on 100% utilization for a day, they produce 20 units, what is their capacity? Okay. And hopefully with a little reflection, you can see that this implies that their capacity is just going to be their output. Capacity equals 20 units. Because they worked all out. They worked at 100% utilization. They didn't take any idle time, any downtime. So that is by definition what capacity means. Capacity means your ability, the maximum output you can achieve. And this is the maximum output they could achieve, right? What if we rephrase the question and let's say now this other guy, this other machine. So if a machine works at 50% utilization, okay, and it produces, this is a different machine producing something else. It produces, let's say, 7 units. Okay, so what is the capacity of this machine? Okay, So hopefully with a little bit of reflection, and you can pause and think about it, you can see that if you work half the time, that's what 50% of utilization means. You're working half the time, you're idle half the time. If working half the time you can produce 7 units, then working all of the time you can produce 14 units, so that's your capacity. Right? And so you can do this again for 25% utilization, you multiply it by 4. So you can see that capacity is really, when you have utilization and output data, is equal to output divided by utilization. Because when utilization is 50%, that's half, or 0.5. You divide output 7 by 0.5, you get 7 divided by 0.5 is 7 times 2, which is 14. If utilization is 25% and a machine produces 5 units, then you divide 5 by 0.25, that'll be 5 times 4, or 20, right? And so capacity is output over utilization. And so we can use this relationship to estimate the capacity of our stations in our simulation. And you only have 50 days of data available in the beginning. So I'm going to insert an empty line. So I'm only going to use the first 50 days of data to do my estimation, because you could do this. You could do this while the simulation is still paused, when you have initial access to it, because you have this first 50 days of data. Okay, so what I need is utilization and output, station 1, station 2, station 3. Because the utilization is changing over time, I'm just going to use an average value. Okay, so for the first 50 days, if I select these cells, first 50 days of data, you can see the average utilization of station 1 is 0.35. So I can just do this, equals average station 1, select the first 50 days of data, and that is 0.35. For station 2, it is going to be this column, 0.51. Station 3, this column, this. And you can clearly see here, let's format these numbers a little bit better, that the highest is station 2, which is the bottleneck. Also, you can see, over 50 days, the utilization was 0.51. But if you look at station 2, the last like 20 days or 15 days, let's go 35, day 36 to the end. Look at the average utilization, 0.74. Because demand is increasing, which is increasing the utilization of station 2. It's getting more and more busy, and it's going towards 1. It's 0.74 in the last 15 days. It's going to go up more and hit 1 soon after day 50. If you go on, see, it hits 1. Day 57 is 1, then it just doesn't come back. So your capacity constraint here, day 57, your capacity constraint. And you can see that that's about to happen, because even the last 3 days of your first 50 days, you're at 1. Okay? But clearly, based on this utilization calculation, the average utilization, station 2 is the bottleneck. Now the output, we have completed jobs. So you can just sum up the completed job over the first 50 days to see how many jobs were produced. And that's 144. And if you sum up the demand over the first 50 days, you can see that the demand was 153. So 153 total was the demand, 144 was the output. So the difference between the two is what's in the queues. So 153 minus 144, 9 pieces are still queued up. They could be, they're probably going to be a queue before station 2, and so on. So station 3 output is definitely 144. Okay. Station 1 output, let's actually check the queues. Okay. Okay, so let's go to our simulator and let's check the queues. Now, remember that when you get customer orders, 60 kits is 1 lot per job. So a job or customer orders, 1 means 60 in terms of the materials. So if you go here, 153 jobs means, 153 times 60 kits that were assembled. And output of 144 jobs means 144 times 60. So let's look at the queues on day 50 to see of the 153 jobs, how many station 1 had completed. So if I go to station 1 queue and I can just look at the queue, this is kits, and I go to all days and I will look at the actual data. So on day 50, it's just 10 kits, which is 1/6 of a job. Okay, so station 2 has produced 153 times 60 minus 10. 10 are still in the queue. So that's how many kits it has produced. And I want to keep everything in jobs because it's easier, because our demand is given in jobs, not kits. So it 153 jobs came in, actually, right? 153 jobs came in, and it still has 10 kits. So 10 over 60th of a job is still not done. So it's actually been able to handle 152.8 of the jobs. Okay, now let's look at station. If you just use 144 here, you'll get approximately the right answer, but I'm just trying to be more exact. So station 1 has handled 152.8 out of the 153 jobs. Okay. Station 3 has handled 144 jobs. We know for sure because that's the output of the whole system. And station 2 has handled 144 jobs because the last station which completes a job is station 2. After station 2, step 4, you go out of the system, right? If you look at the diagram, right, you exit the system after station 2 doing step 4, and the exit right here at the end, we have 144 jobs or customer orders completed. So station 2 has outputted 144 jobs, right, and station 1 has outputted 152.8. So station 3 may have outputted 152.8. They might be in the queue for station 2 for step 4, or it may have outputted less. Okay, let's look at the queue before station 3. Okay, let's look at day 50. And we have 62 kits, which is about one job, divided by 61 point something. So about one job, 62.4. Okay, so, okay, that's what's still in the queue. And so if we take 153, let me just quickly take a look at the queue for station 2 as well. Okay, average kits in queue, go to all days, look at day 50 because analyzing first 50 days of data. 283.86. And here we had 9.94 kits. So this is my queues. Okay, and so I can just be exact. I can do 153 minus how many jobs are in the queue before it. This one, sorry, minus 9.94 divided by 60. So I got 152.83. Okay. Now this station 1 passed on 152.83 jobs to this station, and this many are still in the queue. So this minus this divided by 60 would be 148 is the output of step 2, but then it also has to do step 4, whose output is 144, because we know step 4, the end output is 144. So I'm just going to use 144 here, because this has to do 2 steps. One step is outputted 148, the other step is only outputted 144, so I'm going to take the lesser number. Now this one, because these are still in the queue, and this is also in the queue, some of these are gonna so here this is a little bit tricky to figure out how many did it produce, right? Because obviously this has not reached it and this has not reached it. Some of this may not have reached it either, but if we go by the conservative estimate, this and this and this, station 1 queue and what's before it has not yet reached it. If we assume all of this is step 4 queue, then that has already passed through it, but some of that may also have yet to come to station 3. So this over 60, this has processed maybe 151 jobs. Okay, so here I'm trying to be accurate. To do a rough cut calculation, you can just go by 144. 144 is the number which is the completed jobs. The sum of the completed jobs is 144. Okay, So you can just, for the first 50 days. Okay. So you can just use 150, 144, 144, 144. I'm just trying to be more accurate by building in the queues and using some logic. Okay, this is 10 kids are still in the queue, so it's just handled a little less than 153 jobs. This has for sure handled only 144 jobs in step 4 because that's the output of the system. This is a little bit tricky, so it's not handled these because these have to go through station 1. It's not handled these because these are queued up before station 3. So if I take out these, it could have at most handled 151 jobs. But some of these are also, they are because they have not done step 2 yet, so it's probably done less than 151 jobs. Okay, and so that's some number between 144 and 151. I don't know exactly what. Okay, so you could do it this way or that way. So then your capacity, as we discussed, is going to be output over utilization. Okay. So I take the output and I divide by the utilization. Okay. And this is over 50 days. I want capacity per day. So I'm going to divide this. This is the capacity over 50 days. I'm going to divide this by 50 to get capacity per day. That's 8.58. Output divided by utilization. Okay. And then you want to divide the whole thing by 50 because that's the capacity over 50 days. I need capacity per day. Okay, because I need capacity per day. That's 5.6. And again here, this is an optimistic estimate because I know my actual number is between 144 and 151. And then I'm going to divide this whole thing by 50. Okay, I put it in brackets, divide by 50 to get per day. And that's this. So you can see from the capacity calculation that the lowest capacity is station 2, which is the bottleneck. Okay. Now, if what I did here did not make sense to you and it's only an estimate, you can just do the simple thing, which is to sum up the completed jobs and just use that. Just use 144. So you can just do capacity equals utilization. Let's open bracket, utilization divided by the sum of completed jobs. Okay, and I put $ so it doesn't drag it down, and divide by 50 because I need capacity per day, not for 50 days. 144 is for 50 days. Okay. Sorry, I did the wrong thing. I have to divide 144 by the utilization, not the utilization by 144. So you take the output, 144, and you divide it by the utilization, and then you divide by 50 because you need capacity per day. Okay, and this gives you very similar numbers. You can see, right? Doesn't make much difference. So you can just do 144, forget what's in the queue and try to find the exact output of each station. Just look at the output of the whole system, divide the output of the whole system by individual utilizations, and this gives you a rough cut estimate of capacity, and you can see that the bottleneck is station 2. Okay, so you can just ignore all of this if you want. Okay. So you take the output, divide by average utilization, and the output is the completed jobs that are given in the simulation. Okay, so you already know from this calculation, as well as what we did here, we looked at queues and utilization, that station 2 is the bottleneck. You also know that you're already hitting about 100% utilization in the last few days, or at least very close to it, 80%, right? So immediately we need to buy a machine at station 2. Okay, so the number of machines was 111 to begin with. If I make this into 2 machines, my new capacity for this will be double, 2 times that, because that's the capacity of 1 machine. So if immediately you can buy capacity here by buying a machine, then this becomes your new capacity. And so, what is your next bottleneck? If you buy a machine here, your capacity are 8, 11, and 7. So the next bottleneck, which is coming up, is going to be station 3. So you'll first buy a machine at station 1, And then next bottleneck will be station 3 because, sorry, station 2, not station 1, excuse me, station 2. You first buy a machine at station 2, the bottleneck. It'll double the capacity of station 2, it'll become 11.2. Then looking at these two capacities and this capacity, the lowest capacity now is station 3. And so next bottleneck will be station 3. And so then you'll buy a machine here, which will double its capacity. So it will become that. And so when this becomes 14, this becomes 11, then if you need more capacity, you'll buy a machine at station 1. Right? And then now, whether we need to go up to, if you buy a machine here, then you'll be doubling this capacity and you'll go here. Now, after you buy the first machine, your capacities are 8, 7, and 11. At this stage, what is your bottleneck? Station 3. So your system is going to work at the capacity of the bottleneck. So the capacity of the whole system will be 7.35. Then when you buy a second machine here, so after you buy the first machine in station 2, the capacity of the, let's do this here, capacity of the whole system equals capacity of the bottleneck, okay? So once you buy your first machine at station 2, now the bottleneck is station 3, so the capacity of the whole system is just 7.35. So as soon as your demand starts creeping up to 7, again, you have a problem. Now you have to alleviate station 3. So next bottleneck will be station 3. When you buy second buy will be machine at station 3. When you do that, that will go to capacity of 14. Then you're at 8, 11, and 14. So the lowest is 8. So your capacity of the system then will be 8.08. Okay. And then as the demand creeps up to 8, then you'll have to buy a machine at station 3. And now you'll be at capacity of 16, 11, and 14. What's your bottleneck now? When you have bought one machine at each station. So your machines are 2, 2, and 2. So your capacity is 16, 11, and 14. Now this station 2 is the bottleneck again. And now the capacity system is 11. So if the demand creeps up above 11, again, you're going to have to buy a machine, right? And so you'll notice how the bottleneck keeps moving. Whenever you buy a machine, the bottleneck jumps, right? Because you've alleviated the old bottleneck and something else is the new bottleneck. And so you have to keep chasing the bottleneck as long as your demand creeps up to capacity. When your demand stops growing, then you can stop chasing the bottleneck because now the demand's not going to grow anymore, which is why the demand forecasting is so important, which is why in the PDF, I ask you to forecast the demand. So you can then forecast the demand. You know the demand is only going to grow for the first 5 months. So after day 150, demand is not going to grow. So what is the demand at day 150? That's your peak demand. And that will tell you when you can stop chasing playing whack-a-mole with the bottleneck and stop buying machines. So do you see how everything fits together? So let's look at the demand. This is our demand. And with just the first 50 days of demand, we'll forecast it. So what I'm going to do is select this data. Okay. Insert line plot, okay, and here's our demand. You can just eyeball it to forecast it, but it's better to just click the data. So you see the data is highlighted. Let me see if I can change the color of the line. Maybe this. Okay, now you can see those points. Okay, so it looks gonna this a little bit better. You can see the points. So when you select the data, you can right click it, add trend line, display equation, display R squared. And so this is your regression equation you can use to forecast your demand. Okay. Now, why is this regression equation good for forecasting? Because we only have trend right now. There's no seasonality. The write-up, if you go to the write-up, that's why you read the write-up carefully. The write-up does not talk about seasonality. The only thing it tells you about demand is on page 2 right here, which talks about an increasing trend for the first 5 months. And then the demand is supposed to peak. And so with the information we just have a trend. So regression is great for trend. And so we can use this equation. So our forecast equals to 1.1118, the constant term, plus 0.0764 times the day. Okay. And this is going to forecast the average demand. Notice the demand goes up and down. It's very variable. It's highly variable around this trend line. But this trend line will give us the average demand. Okay, so let's forecast on day 150, which is 5 months, because the write-up tells us that demand can grow up to 5 months, right? So what will be the demand at, so our forecast for day 150 is going to be this equation, 1.1118 plus 0.0768 times 150. So we expect the average demand on day 150 to exceed 11. So you may have to buy a third machine here, right? So even before the simulation starts, I'm doing all this, remember, I'm doing all this analysis with first 50 days of data, and the simulation has not even started playing yet, right? Because the simulation is paused and you have first 50 days of data available, and then when the simulation unpaused, you're on day 51. So even before day 51, at day 50, when the simulation is still paused, you know all of this. You know what is the bottleneck. You know what order you need to buy machines in. First buy at station 2, then buy at station 3, then buy at station 1. And your forecast is telling you, even when you buy a new machine at each of the stations, and now your system capacity is 11.29, you're still going to have to buy a third machine because your demand is going to exceed 11 on average. And the peak demand is obviously going to go way over 11, because if you look at it here, the demand can be twice the average level. When the demand is averaging 5, the peak demand is going above 10. So if this is the average demand, the peaks can go as much, double that almost, go up to 25. Okay, so we need to buy a third machine. If you buy a third machine here, then your system capacity would be 14.7. That's above 12, so maybe that's fine. And then you have to think about, okay, if you buy another machine here, the system capacity will go up to 16. Do you really want to buy another machine to go from 14.7 to 16? That's a very small jump in capacity. Why? Because when you buy a third machine here, this station jumps to 22, but now this is the bottleneck, right? Then this is the capacity of the system. So buying this another machine here is, I don't think it's worth it, but you can do break-even analysis. You can look at the price of the machine, how many extra orders you'll be able to process, will be the revenue on that order. You can do all that calculation and see the cost-benefit analysis for that, right? But at least you probably will end up at 232 setup eventually, right? And you don't want to buy machines too early. As you hit the bottlenecks, as you hit capacity constraints, you want to buy a machine before you hit a capacity constraint so you don't lose any revenue. But you also don't want to buy too early, because your extra cash earns interest, and that's money that you earn. So you don't want to buy too early. Okay, so that's with the simple analysis, we already have a plan laid out on which station we buy the machine first, what to do next, right? Okay. Okay, next we know how to identify the bottleneck. We know how to determine what the bottleneck is based on the queues or the utilization. We can actually do capacity calculations and compare with the forecast to make a plan on when to buy machines, right? So we have done a lot. We just need to look at a few small things before we can close up, okay? One thing I want to show you, because this will often happen to you, okay? People will buy a machine and they'll say, nothing is happening. It made no difference, okay? Let me show you something. Look at the demand. Okay. The demand starts falling after about day 236, maybe around that 236, 240. Demand is falling pretty sharply. Average demand, right? Okay. Now look at this. The output of your factory, jobs completed, is not dropping. How can demand be falling at the end and the output of my system is not falling? Shouldn't it fall with the demand? Shouldn't I be outputting less jobs if I'm getting less jobs in? What could explain this? Pause the video, rack your brains. The answer is queues. You had so many queues built up that even when the demand starts to fall, you're still eating up into the old queues, the old jobs that have queued up, that you're still outputting at the same rate. The queues are exactly the reason why if you buy a machine late, I'm going to write it in red. If you buy a machine at a station late, what is late? Late means queues have already built up. There's a massive queue before the station. That means you're late. You are not proactive. So they're massive queues. Okay? The result? Utilization will not fall. Because if a machine is 100% utilization and you buy a station is 100% utilization, you buy an extra machine, its capacity is gone up, utilization should fall now. With the extra capacity, you have more capacity than demand. You should be idle some of the time. Utilization should not be 100. So why is your utilization not falling? Because you have queues built up. Now, even when you have added capacity, the added capacity is eating through the queues. Until it empties out the queues, it's not going to fall. The utilization will not fall. So I'll often get an email, hey, professor, I bought these extra machines, and some people panic and they buy an extra machine everywhere, like at all stations. Oh, I bought an extra machine at all the stations. My utilization was not falling. I bought a second machine. I bought a third machine. My utilization is still 100%. What is going wrong? The simulation is wrong. It does not make sense. What is happening? So when I get an email, panicky email like that, I say, look at your queues. You have way more capacity than demand now. You have too much capacity, but you're still eating up the old queues that you built up. This extra capacity is munching through like a cookie monster. It's going through that queue, but it's still going to take a few days to get through the queue. And then your utilization is going to hit rock bottom because you bought too many machines now and you didn't think, right? So if you have a queue built up and you add an extra machine, your utilization will not immediately drop. It'll stay at 100% until you eat through the queue, and then it will fall below 100%. Unless by the time demand has risen so much that you're back again at 100%. So because demand is also rising, right? And so the extra capacity is eating through the queues, but the demand is coming up to meet the capacity. When it gets near capacity again, queues will start to build up. So, as long as you're proactive, you buy machines on time. When you buy a machine, you'll see the utilization drop, okay? If not, check the queue. You'll see the queue drop at least. When you buy a machine, queue should drop, right? It'll start eating up the queue will drop, and as the queue drops, eventually the utilization will start to drop. So do not panic, stay calm, and carry on, okay? Another question I get, and that's the same reason. Queues are the same reason why the output is not dropping at the end when the demand is falling of the do-nothing team. Now, conclusion, okay? By this time, through scenario 1, through all that analysis, you should now understand relationships between these important quantities. What relationships you should understand? You should between queues, capacity, demand, utilization, and lead time. Okay, so what is the relationship between capacity and demand? The relationship is when demand is bigger than or equal to capacity, it leads to queues, right? What is the relationship between queues and utilization? If you have high queues, it's going to lead to 100% utilization even if your capacity was increased until you munch through the queues, okay? What is the relationship between queues and lead time? Okay, as your queues blow up, your lead time blows up because so much product is spending time waiting in the queue. That's added to the lead time. Waiting time is part of your lead time. So if you spend a lot of time waiting in the queue, lead time blows up, you get less revenue from the customer. So if you want to get the maximum revenue from your customers, you want to keep lead times under the promise of contract 1 or whichever contract you're on. If you want to keep the lead times low, you got to keep the queues low. How do you keep the queues low? Your capacity must be bigger than demand. How do you keep capacity bigger than demand? You have to know where the bottleneck is. How do you know where the bottleneck is? Watch this video again. Once you know the bottleneck, alleviate the bottleneck by buying capacity, keep capacity above demand, keep your queues low, keep your lead times low, make money, right? So you should understand all of these relationships, and that is what you are supposed to learn from scenario 1, okay? And so now you should go into scenario 2 and be able to do an A+ job at capacity management. Scenario 2 is more than capacity management, right? Scenario 2, you can change contracts and you can manage inventory as well. So in scenario 2, you'll be able to go to your orders, the demand area, and you'll be able to change this contract. But the newer contract will have less quoted lead time. So don't change the contract if your lead time is blowing up, right? You'll also be able to go in here and examine scenario 2. The inventory graph may not look so nice. It may be problems there. You may have to adjust these parameters to fix inventory. So there'll be new things in scenario 2. But then you'll also have the capacity management part of scenario 2. So at least you should be acing the capacity management part of scenario 2, because now I've explained to you in great detail everything you need to know about that. So that is all for this video. Watch this carefully, take notes. As long as you understand these relationships between queues, capacity, demand, utilization, and lead time, you should be fine.